So here we've got HA, which is just the formula for a generic acid. We don't know what acid this is, but we know that the H component is the hydrogen that's going to dissociate off. And we have the A here, and the A stands for anion, because once it dissociates off, what's left is that anion. So we have this acid setting up an equilibrium with water, forming H3O plus and that A minus anion. So since this is establishing an equilibrium, that tells us that this HA here is a weak acid. If it were a strong acid, we would see full dissociation. In other words, the reaction would only progress to the right. There would be no equilibrium to set up. So since this is an equilibrium, that means you can set up an equilibrium expression for it, meaning K equals the concentration of the products, which in this case are H3O plus and the anion A minus, over the reactants, in this case, the concentration of the undissociated acid, and you're going to leave the water out of this equilibrium expression because you don't ever put liquids into an equilibrium expression. So this is the equilibrium expression here for a generic acid reaction at equilibrium. Because of that, we're going to call this Ka, yet another example of K. Where these Kas are useful, well, before I get there, first we need to think about the size of these Kas. Kas are going to be small, and by small we mean less than 1. And if you think back to last unit and what that means, when your equilibrium constant is less than 1, that means you're heavily reactant favored, which makes sense. This is a weak acid, and since it's a weak acid, very few of them are going to dissociate, meaning the left side will be favored. We can actually take this a step further by using Kas to compare the strengths of weak acids. So here in the red on the left, we have Ka1, which is just the equilibrium constant for some weak acid. And on the right in blue, we have Ka2, which is a different weak acid's equilibrium constant. We know they're weak acids because both of these Ka values are small, meaning that favors them not dissociating. Only a few of them will dissociate off their H's. Now, we can actually compare these Ka values, and it's pretty straightforward. The larger the Ka value, the stronger the acid. So all we've got to do is compare Ka1 to Ka2 to see which is stronger. And it turns out Ka1 is greater than Ka2 in this case. So Ka1 is the stronger weak acid. It's important to know they're both still weak acids, but Ka1 is the stronger weak acid. Now, another way we can compare these is actually by something called the pKa. And just like pH, the pKa is the negative log of the Ka. The only reason we do this is because when you take the negative logs of these small numbers, like these Ka values, it makes them easier to compare. So for example, pKa, this is for acid number 1, equals the negative log of Ka1, which in this case is 2 times 10 to the negative 5th. And when we plug that in, we find that pKa1, or in other words, the first acid's pKa value is 4.7. Over here in the blue, we'll repeat the same thing. pKa2 is equal to the negative log of Ka2, which is 8 times 10 to the negative 7th. And we find that pKa2 comes out to be 6.1. So now we can just compare pKa values to see which is the stronger acid. But since we've taken the negative log of it, our way of thinking has been flipped. And instead of the larger value being the stronger acid, now the smaller pKa is the stronger acid. So since pKa1 is less than pKa2, in other words, 4.7 is less than 6.1, again, that leads to us knowing that the red acid on the left is the stronger acid. The same can be done for bases. Here we've got an equilibrium established where NH4 is acting as a base. So if we set up an equilibrium expression for this, it would still be K, but this time, since we're talking about something behaving as a base, we'll call it Kb. And it still equals the concentration of the NH4 plus over the OH minus concentration, all over the reactant NH3 concentration, and again, water doesn't appear in it. Just like on the Ka values, your Kb values are small. And by small, we mean less than 1. Because these are weak bases, the left side is going to be favored, so that supports a K value of less than 1. And just the same, you can take the negative log of that Kb value in order to find pKb. So one last thing to look at. Whenever you have a weak acid, it has a given Ka value. If you look at the Kb value of that acid's conjugate base, so if this is some weak acid, it's going to release a hydrogen to form some conjugate base. Whatever that weak acid's Ka is, its conjugate bases, Kb, when you multiply them, must equal Kw. Well, just as a reminder, Kw is 1.0 times 10 to the negative 14th. So let's say we're using this value for Ka right here. If this acid has a Ka value of 2 times 10 to the negative 5th, we'll plug that in here for the Ka of the acid, 2 times 10 to the negative 5th. And then close that parenthesis. And multiply that by this acid's conjugate bases, Kb. And since we don't know that, we can actually solve for it and figure out what the Kb is for the conjugate base of this acid, which turns out to give us a Kb value of 5 times 10 to the negative 10th. Now, when you kind of think logically about this, this makes sense. This value of Ka is going to be larger than this value of Kb, because the stronger the acid, the weaker the conjugate base. If this Ka value here had been teeny, 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 tiny, it would have forced this Kb to be large, which again makes sense. If it's a weak acid, it would have a stronger conjugate base. And one last thing to consider, since we know Kw equals Ka times Kb, we can actually take the negative log of both sides. The negative log of Kw equals the negative log of Ka times Kb. And you might have to go refresh your properties of logs here, and you don't have to ever derive this on your own. I'm just showing you how it's deriven, if that's even a word. The negative log of Kw, well, that just turns out to be 14. And then when you break this up, the negative log of Ka times Kb is the same as the negative log of Ka plus the negative log of Kb. So 14 equals the negative log of Ka, which is pKa, plus pKb. So if you know an acid's pKa value, it's very easy to find its conjugate base's pKb value.